Welcome to the video on crystal oscillators. In this video, we are going to discuss about the crystal oscillator and what are the types of crystal oscillators. So first we can discuss about the basics of crystal oscillators. What is meant by crystal oscillator? A oscillator which uses a crystal to generate a frequency is called as crystal oscillator. So we all know the basic principle of crystal oscillators is depends upon the piezoelectric effect. So piezoelectric effect is an important 2-mark question, and we already studied about this effect in 12th standard physics. So in the next slide we can discuss about what is meant by piezoelectric effect. And here the crystal used in the crystal oscillator, it will exhibit a property is called as piezoelectric property, and the general shape of the crystal can be given as hexagonal. When a crystal wafer is cut perpendicular to x-axis, it is called as x-cut, and when it is cut along y-axis, it is called as y-cut. And now you are seeing the symbol of your crystal and the equivalent circuit of your crystal. So here a source and the crystal can be placed. The crystal which was holded by the plate, so these two are called as crystal plate, and this is what crystal slab. So these two are holding plate and this is what crystal slab. Now we are seeing the equivalent circuit of a crystal. A RLC component are connected. So this resistor, capacitor and inductor both are connected in series along with one capacitor is called as CM. So this capacitor is parallel with this 3 component. CM is called as mounting capacitance. Yes, and now we can discuss about what is meant by piezoelectric effect. So in this crystal oscillator, whenever we apply a mechanical vibration, okay, so whenever you apply a mechanical stress or mechanical vibration in any one of the phases of the crystal, it will generate a small voltage or it will generate a potential difference. Okay, so that is what I mentioned in the first slide. When a mechanical stress is applied across one of the faces of the crystal, a potential difference is developed. So simultaneously, when a potential difference is applied any one of the phases, it will develop a mechanical stress or mechanical vibration. So it is when a potential difference is applied across one of the phases, a mechanical stress is produced along the other phases. So this is called as piezoelectric effect. And here in this crystal oscillator, we can use the materials like rock salt, quartz and tourmaline. So the most common crystal can be called as quartz crystal, because quartz crystal is the most commonly used crystal and it is very inexpensive and it is easily available in the market. And now you are seeing the slide, the frequency response. So the frequency response of the crystal oscillator. So here this dotted wave, sorry, this solid line wave can be called as Fs, that is series frequency, and this waveform, this one, okay. So apart from this dotted line, so this is called as Fp, that is parallel frequency. So when the series frequency will be occurred, it's very simple. So whenever the reactance of the inductance is equal to the reactance of the capacitance, the series resonance frequency can be formed. And the normal frequency of oscillation expression can be given as, for crystal oscillator, the frequency of oscillation can be given as F equal to 1 by 2 pi into LC, because crystal oscillator is one type of LC oscillator. And next we are going to see about this parallel frequency. So the parallel frequency, when it is occurs, means whenever the reactance of the RLC is equal to the reactance of the capacitor Cm. Okay, so this is what capacitor Cm. So mounting capacitance, actually this the value of mounting capacitance is slightly greater than this C. Okay, the value of Cm is very high compared to this C capacitor. So now the expression for parallel resonant frequency can be given as Fp equal to 1 by 2 pi root of L into Ct, where Ct equal to C parallel with Cm, that is C into Cm by C plus Cm. Yes, and as I before told that the value of this mounting capacitance Cm is very large compared to the capacitor C, and the value of Ct is approximately equal to the capacitor C, and the resonant and the series resonant frequency is approximately equal to the parallel resonant frequency. So almost this Fs and Fp may be equal. So that is what Fs equal to Fp. So now we are going to discuss about what are the types of crystal oscillator. So basically there are two different types of crystal oscillator. The one is called as Quartz crystal oscillator and the second type is called as Miller crystal oscillator. So, and this is the circuit diagram of Quartz crystal oscillator. So please listen the circuit for 3 seconds. Okay, please see the design of the circuit. Yes, so this circuit is very similar to the Colpitt's oscillator. It's very similar to the Colpitt's oscillator. Okay, so what is the difference? What is the difference in this circuit? The only difference is in the Colpitt oscillator, instead of this crystal oscillator, we can use one inductor. But here, instead of inductor, we are using one crystal that is called as Quartz crystal oscillator. So the Colpitt's oscillator can be modified by using the crystal to behave as an inductor. So this circuit is called Quartz crystal oscillator. So the crystal behaves as an inductor. Yes, and these two capacitors C1, C2 is needed in the tank circuit along with the inductors are used in the Colpitt oscillator, but here we are using a crystal. So that is called as Quartz crystal oscillator. So now we are going to see the working principle of Quartz crystal oscillator. So the working principle is very similar to the Colpitt's oscillator. In the previous video, I explained the concept, principle and the derivation of Colpitt's oscillator. So please one time see the video of Colpitt's oscillator and please get the working principle. Anyway, I will explain. So in this Quartz crystal oscillator, this resistance RB1, RB2 and the RE, it will provide the DC bias, and the capacitor CE is emitter bypass capacitor, and this RFC is called as a radio frequency choke, and it will provide the isolation between AC and DC operation. So it's AC and DC operation, and this is the power supply, and here it is your output voltage Vout. And this is the modified circuit of Quartz crystal oscillator. So here this oscillator circuit can be modified by using the internal capacitors of the transistor. Here there is no C1 and C capacitors are present. Here we are using a internal capacitors of the transistor called as C. So the separate capacitors C1 and C2 are not required in this equivalent circuit. So it is a crystal oscillator. This R1, R2 are the biasing resistance, and here RE is the emitter resistor and CE is the emitter bypass capacitor. So basically the crystal oscillator has a good frequency stability, and also it is used in computers, counters, basic timing devices, in the electronic wristwatches, etc. Okay. And the next type of the crystal oscillator can be given as Miller crystal oscillator. And also please see the circuit diagram for 3 seconds. And this circuit is very similar to the Hartley oscillator. It is similar to the Hartley oscillator. And what are the modifications? Okay, the only one modification is in Hartley oscillator, the tank circuit of the Hartley oscillator, we have two inductors and one capacitor. Here one capacitor will be present and one inductor will be present. Instead of second inductor, we are using a one crystal, one quartz crystal here. So this is the circuit of Miller crystal oscillator. In Miller crystal oscillator, it contains one capacitor along with one inductor. Instead of the second inductor, it have a quartz crystal, and this Cc are the coupling capacitor, and R1, R2 are the biasing resistance, and Re is the emitter resistance, and Ce is the emitter bypass capacitor. So the working principle is, again, it is almost same as Hartley oscillator, and here this crystal behaves as other inductance L2 between the base and ground. So the internal capacitance of the transistor act as a capacitor to fulfill the elements of the tank circuit. So on this crystal, it is a very important crystal. It will decide the operating frequency of the oscillator. It will decide the operating frequency of the oscillator, but usually it will provide the low output power. So this Miller crystal oscillator is not used in high frequency applications. Okay, so it will be used in the applications like only common applications like trigger circuits, sawtooth generators, phase control, and timing circuits. So that is the main applications of this Miller crystal oscillator. So overall, the Pierce crystal oscillator is similar to Colpitt's oscillator, and the one modification is, instead of one inductor, we are going to connecting one crystal, and for Miller crystal oscillator, it is similar to Hartley oscillator. Instead of second inductor, here we are connecting one crystal oscillator. And now we are going to discuss about the comparison between LC oscillators and crystal oscillators. What is the comparison? Okay. So for LC oscillator, the frequency is dependent on the values of L and C, and for crystal, the frequency will be dependent upon the crystal. And usually LC oscillators preferred at high frequency, and for crystal it will be preferred at high frequency again. So it is very high frequency, and this is also high frequency. And the types of LC oscillators can be given as Hartley, Colpitt's, and Clap oscillator. And the types of crystal oscillators can be given as Miller and Pierce crystal. And for LC oscillators, it have poor frequency stability except for the Clap oscillator, except Clap oscillator and the Hartley and Colpitt, which will give a poor frequency stability. And for crystal oscillator, it is a very high frequency stability. And the applications are TV, frequency sources, and frequency synthesizers. And the applications of crystal oscillators are crystal clock, frequency synthesizer, and special types of receivers. And finally, we can conclude with this slide, applications of the oscillators. Okay, what are the applications of the oscillators? So actually, oscillators are the most common element for all electronic circuits, and it is very important element because it is used in very numerous applications. So here it can be used as in the computer peripherals, timers, calculators, PLL, that is phase lock loop, multimeters, oscilloscope, and many other applications. That is the main applications of the oscillators. Thank you.